Hi, good morning. My name is Luca Deri, and my colleague Samuele will be talking together about eBPF in the context of network traffic monitoring. So the idea is to use and to show you an application of eBPF to something meaningful. We are not talking about eBPF per se, but how to use it in a word. So let's start with a few notes about us. I'm the founder of the ntop project. You heard this before when we talk about pfring. I'm also a lecturer at the University of Pisa. Samuele is a former student of mine and is working with us at ntop. ntop is an open source project I started in 1998, so very long time ago. It was about monitoring network traffic in a simple way. Don't think about the internet. Okay, the internet did not really exist as it is today. Okay, it was a totally different world. So over the time, we started from analyzing packets, okay, just to display to people, to accelerating packet capture, so pfring. We have done many other things. Another thing, a good contribution, I think, to the open source community is a library called NDPI that allows you to analyze and dissect packet payload. So it allows you, for instance, to tell you what is the application protocol of a certain communication. So this is called NDPI. You can find all our open source code on GitHub, so github.com/ntop. And so this is the place where you will find our activities. Let's start from the very beginning. So why we're here talking about network monitoring? So when we talk about network monitoring, so this is a definition coming from Techopedia. So we are talking about the ability, in essence, to monitor a computer network to see what is happening. Okay, so if there is something wrong, unexpected, so from the security standpoint, from the configuration, misconfiguration, this type of things. And usually the way to do that is through packet capture. So in essence, we capture packets, we analyze packets, we report users what is happening. This is why, for instance, I started pfring, because it was a way to accelerate packet capture. Packet capture has always been, the main problem. So we have to receive this data. So the input are packets. So if you talk about that, so look at this picture, 2009, so 10 years ago. Okay, this was the picture of the ntop world many years ago. So pfring was there, so we had a different way of polling packets, a better packet poller, TNAPI, and then we have all our application on top of it. Okay, so here we are talking about packets. We are talking about network adapters. We are talking about way to accelerate packet up, and then we have packet analysis. Again, 10 years ago. If you're talking about 2019, you go to GitHub, you download ntopng, so that is the successor of ntop, so the next generation. You will see a graph like this. You will see that there is a peak. You will see that there is probably an anomaly here. And you will see that packets are still first citizen. This morning, until now, we talked about packets. XTP, DPDK, and so on. Packets, packets, packets. Because packets are too many, so it's not possible really to handle packets easily, so you have to put them in a meaningful fashion. So in a way so that you can understand what is happening. Usually the way of doing that is through the concept of flows. So you put together, one after the other, packets with the 5 tuple. So same protocol, same IP source, destination port, and so on. So this is the, let's say, uncompressed version, so you will see packets. This is the compressed version, flows. So you see my PC is talking with that PC over port 80, and all the packets of the same common action will be put together. And again, people like to see a peak. Again, there was a peak here. You want to say, hey, what's happening? You can see the flow. But if you don't trust flows, so if you want to go down to packets, in ntopng you can click and say, give me the packets. So again, we're talking about packets. What's wrong with packets? I'm not against packets. For all my life I've done packet analysis. So it is good, okay? In particular, it is good if you want to be outside of the system you're monitoring. So we are here today at FOSDEM. So if I want to see what is happening in this room, I cannot put an agent on every single laptop. First of all, because it is impossible. You have a smartphone, you have tablets, you have many things. So it's very easy to look at packets, so capture packets, classify them, put them on a web interface. Very good. However, there are some challenges. For instance, one is encryption. In NDPI, we had to struggle fighting against that. Not that we have to decode the packet. Again, deep packet inspection is not about decoding and dissecting the packet and extracting, your data. It is about understanding if you're talking about Gmail or if you're connected to your, home application. So we had to, for instance, to decrypt the initial, certificate exchange to understand what is that about. However, there is virtualization. So in the past, computers were, connected to the internet, but these days, you have seen Cilium before, you will see a big machine with several containers, all providing a service, actually a microservice, and all interacting. Sometimes the container moves on another place, and so on. So if you look at the packets entering or leaving a machine, at the end, you will see the same result. So you will see that you're connected to a certain website. But you don't understand the interaction of things happening inside the same computer. This is the main problem. And also, when you deal with packets, you have to handle fragmentation, packet loss, retransmission. So the packet is not the native way of communicating. When you open a socket, you say, I want to connect to this port, I want to send get / whatever. You don't know anything about packets. Okay? So you don't have to pay attention to IP address, nothing, zero. It's the card that is doing for you. If there is a long MTU, it will split the packet into segments and so on. So anyway, packets are nice, but they're not native. People don't understand packets. I mean, experts know what they're about. So years ago, I wanted to extend that and give more information about the system introspection. I wanted to handle virtualization. I wanted to have also an ability of have a continuous drill down from a problem, let's say a peak, and say, what is happening? Okay, my web server has talked with MySQL, and this was the reason. And then you go to flows, you go to packets. So at the end, we are still using the same flow and paradigm, packet paradigm. But I want to see what is happening inside the system. If there is a security issue, today you can see, oh, I've seen this very nasty payload inside my packet, but you don't know the application that has sent that payload. You don't know who has to receive the payload. You simply have an IDS or an IPS that is reporting that. But you are blind with respect to what is happening inside the system. So we want to fix this problem. So this is what we are going to talk today. So in 2014, I was very excited because I'm a good friend of the creator of Sysdig, about Sysdig. I don't know if you are familiar with that. Sysdig was, it is still a kernel module that you can install on Linux. It looks like a TCP dump for system events. So in essence, you can look at system events. You can see connect, close, send, receive. So the idea was to give an idea. So when we have, application or containers talking each other, to see, okay, my HTTP has talked with MySQL, and this is the amount of data that has exchanged. However, this software, that again in 2014 was very, very nice, was designed by somebody that had packets in mind. Packets. Okay, this was the idea. So use TCP dump over Sysdig. This was the problem. So we had, so this code is still available. We integrate that with Elasticsearch. You can see the nice graph, top owner, top processes, top of thing. Okay, very nice. So I spent a real lot of time on that, but it was a failure. It was a very big failure for many reasons. First of all, it was using too much CPU. So you have a process that is using 10 to 20% of the CPU on your box, simply because Sysdig was designed with the packets in mind. So if there is a system that receives a lot of traffic, you have to analyze a lot of packets. And that is wrong. First of all, because you are loading the machine with the packets anyway, because there is a lot of things to do. And second, because adding your monitoring feature adds extra load on the system. Second, people don't really like to install agents. Okay, it's not always possible, like I've said. But again, this is still doable. But the main problem is that Sysdig requires a kernel module. And many people buy commercial support, buy Red Hat or whatever. And these people say, if you install a kernel module, then you are on your own. People also don't like that. And also containers were not that popular in 2014. Docker started to exist, but was not a big problem at that time. So we were a little bit ahead of time. But the main problem was the CPU. I mean, monitoring was too expensive. And this was the problem. In essence, a sysdig, how it works, just to give an example. So you suppose that you want to monitor a TCP connection. You have to track socket, you have to track send, receive. Then you have to put them together in flows, similar to flows, and then you have to report the information. And this is very CPU expensive, because you have to analyze every single packet. That is the problem. So sysdig is too much packet-oriented. Now I'm going to leave the microphone to Samuele.
Hi everyone, I'm Samuele and I studied the application of eBPF to traffic monitoring with Luca. So eBPF is a very great tool that enables us to inject code inside the kernel and have it executed when a specific target kernel function is invoked. And so this, by attaching eBPF code to network functionalities, we are able to avoid inspecting, capturing and analyzing the single packet, but focusing only on the events we are interested in. Furthermore, because the code is executed inside the kernel, we can compute metrics and send it to user space only the things that are needed, and avoid sending all the information we can collect. And both these features gives us a great savings in terms of CPU usage. Furthermore, BPF has another key feature that is that it doesn't need the installation of another kernel module, but becomes embedded in the modern Linux kernel versions. So this is very great things. What we have done is inject BPF code inside the kernel, is set up inside the kernel, and generate events and send it to user space through a circle buffer provided by BPF. So the structure of events is very simple. It's articulated in different ways, but provide very simple information such as the destination or source port and IP address, the protocol, or for example the latency calculated from inside the kernel. So is from the perspective of the kernel or the application, and not from the external point of view of who captured the packet. Another thing that we are providing is the PID, the user ID, or for example the full path of the executable, or the task name, or the executable, or the process name, or for example the time in which the packet, the event has been triggered, and things like this. So to do this, we attach the different probes, we inject code we attach code to different kernel functions that are, for example, the TCP connector, which is triggered when the kernel connects to a remote or local host, or for example to intercept UDP or events concerning the change in the state of a socket. For example, we can track when a socket is closed and analyze how much bytes has been received or sent through that socket. Another thing that we can capture is the retransmissions, the events regarding the retransmissions, and this is it. So to gather this kind of information, what we've done is using a BPF helper function, that is BPF get current task, to obtain the task, the struct associated to each thread and process. And by navigating through the kernel structures, we can collect this kind of information, such as the user, or for example the cgroup, and furthermore, by using the socket that is provided with the function call. For example, when we connect, we use the TCP connect, we provide as argument the socket that we want to use. By analyzing the socket, we can extract information regarding the protocol or the destination address. So to provide visibility concerning containers, what we have done is using the cgroup that we collected from inside the kernel to interact with the Docker daemon, with the Docker API, and gather information concerning the container. This can be done because the cgroup identifier that we found that this group identifier that we have extracted from the kernel structure and sent to user space is the same identifier that Docker used to track containers. What we have basically done is collect this information, collect the cgroup identifier, send it to user space, and at user space level, interact with the Docker daemon to collect information and store them in a cache. So we can we have information like, for example, the container name or for how much time has been the container alive. Furthermore, we have found that from the result of the query, we can obtain information from Kubernetes, such as the pod, or the cluster where the container is in. So we have a greater view about what is going on the machine in a bigger way concerning Kubernetes, in a Kubernetes view. So under the hood, TCP accept has been implemented very simply because we attach a probe to the return of the function call. So when the function returns, our code is executed. When our code is executed, we use the socket that is returned by the function to collect network information, and use the task structure to collect information of the user and concerning the process. So in a very similar way, we have tracked retransmission and events concerning socket closed when a socket is closed. But for the connect, it has been more difficult. Indeed, we have to use an hash table because we want not only to return information about the user or the network, but we want to return also the return code of the function to check if it has failed or it has been successful. So what we have done is attach a probe when the function is invoked, when the TCP connect is invoked, collect the socket that is passed as argument. Then the function is executed, the controller returns to the function, and when the function returns the return code, our code is executed again. We check in the hash table where we put the socket, and is indexed by using the thread identifier. We get the socket and track network information beside the return code. And in this way, by putting also the kernel time, we were able also to measure the latency of the connection. Okay. Okay, allora vai. Okay. Okay.
So in essence, we have integrated eBPF with ntopng through a library called eBPF flow that allows us to avoid seeing all these internals of eBPF and just to report events. Just to give an idea, this is a typical example. So you start eBPF flow. This is a helper. It allows you to see, the kernel time, the process ID, what is happening, who's talking to who, what is the process, what is the command, something like that. So the idea is that we want to make this library available also to everyone, so that you can put your application on top of it and forget eBPF. So for you, it will be a source of information. So currently in ntopng, this is a preview of what we have. Allows you to see next to the communication also the user and the process that is executing that. So you will see this packet is going to Apache, okay, or this packet is coming from a Chrome thread. And this is for the source and for the destination. Of course, thanks to the packet inspection, we can analyze that. This is very important because it allows us to augment the information. So we have an idea of what users are doing. So what am I doing? Okay, I run in Thunderbird, so I'm using Dropbox. So this is how I use my network. So not just analyze packet, but also analyze the information. So activities. So what is a certain user is doing. And I don't know if you have noticed, but we have the full path of the application. So in case you will have, let's say, a security violation, you will see that a certain packet is very bad. So you know exactly the process that has created that packet and the user and the container eventually. So this is important. We have also the ability of putting all these things together. So you see, what a certain process is doing, what are the process activities, and what are the users doing inside the container. But this is very nice. Okay, we just track some events, very simple. So if you have a gigabit of traffic, we simply see connect, response, and periodic update. But we have a problem with UDP. Inside UDP, every packet is independent. So you can open a socket, send a packet to each of you. So how do we avoid playing with packets again? How do we avoid sending to user space an event for every single packet? So at the moment we have used an in-kernel LRU, so that whenever we see packets, similar packets from the same to the source to the same destination, we just send the event once, okay, every time. So let's say for every second, for every 10 seconds, we see several packets. So especially if you have a VPN, let's say before somebody mentioned OpenVPN. So this is a typical example. So we send an event every few seconds, so without doing that. So this is one of the problems that we are still trying to tackle. Unfortunately, everybody is talking about eBPF in very positive terms, but there are also some problems with it. The first problem is that BCC is not what I consider a stable tool. First of all, there are some limitations in terms of memory, loops, this type of things. You might say, so why is it a problem? It is a problem because whenever you have to decode a packet, you have to know, you have to go through certain layers. So in fact, before in the presentation of XDP, people put a lot of emphasis about the speed. Say, I'll give you this packet, give me this packet. But if you have to look at the packet before making your decision, so you have to decode it. If you want to decode it inside the kernel with eBPF, you have to deal with the problem and the limitation of this type of tools. Another point, for instance, is that the BCC tools are changing very often. Okay, so you see people that are playing with Python and they are happy. But if you play with the C API, sometimes this might change. We have also some other little limitations that I hope that will be solved in the future. So just to wrap up, it is now possible to see the full path from packets to activities. If there is something bad happening, I will not say this packet is bad, but I will say this user with this process has created the problem. That's it. Thanks to the container paradigm, and thanks to the fact that our library can run on the host, not on each container, so we have the ability of monitoring all the containers of a system and to collect this metadata and attach this to packets. The load is very little. With our tool, the load is less than 1%, so it's almost unnoticeable. And we have this information. This one showing this preview, it will be part of the next ntopng version 4. But we plan to have this library available so that there might be other tools willing to use it. So that, for instance, I imagine a network probe or an IDS that want to add this information next to their problems they are reporting. Thank you very much.